So here's a problem from Hibbeler 4.62. Determine the magnitude of the force F in the cable AB. So here's your cable going from A to B. Determine the magnitude of the force in order to produce a moment of 500 foot-pounds about the hinged axis CD. So you've got your force goes from A to B, you've got an axis from C to D, so that's kind of like a door that's on a hinge there, and you know the magnitude of the moment about that axis and want to know the force. Okay, so this is moment about an axis, right? Not moment about a point, so you have to be careful. Moment about an axis, right? The hinged axis CD. So moment about an axis, anytime you have a moment about an axis, so let me write it like this, MCD, that's the moment about that axis CD. You're going to use this kind of form, U hat dotted with R cross F. So this thing here is the usual moment, right? But then I have to project it onto a particular axis, right? So what U hat, the U hat is defined by the axis, so I need CD here. And then R cross F. So F is pretty clear, it's the force that goes from A to B. The question is, what R do you use here? And in fact, I'll tell you a little trick, is that R can be any vector from the axis to the line of action of F. Okay. So basically any vector that starts on this line and ends on this line is what I can use for R. Okay? Okay, so now our plan is just to write each of these things in Cartesian components and then to use the cross product and dot product. I should say before I go on that the problem is really missing a word. It says to produce a moment of, what should be here is magnitude. 500 foot-pounds around the hinged axis. Okay, so let's start writing down the Cartesian components of all of those vectors. Okay, so first things first, let's deal with this unit vector. That's RCD divided by the magnitude RCD. And I won't deal with numbers, so I'll just put in non-zero components. So I need a vector which goes from C to D. C is at the origin, so this is at the point 0, 0, 0. So what I'm going to have here is y d j hat, so that's the y component of point D, or y coordinate of point D, plus z d k hat divided by the magnitude of that, which is yd squared plus zd squared. Now we need R, some vector that goes from the line, from the axis to the line of action. So maybe the simplest one that I can see is one that just goes from C to A. I mean, but any of them are good, so I'm going to use this. R CA is pretty straightforward. I just need a vector that goes from C to A, and that just has one component, XA I hat. There's no Y or Z components to that. Finally, we need the force F. So the force F is acting along this line of action. So let's write it like this. F, that's the magnitude of the force, and then the direction is defined by this vector which goes from A to B, right? So now we have to do the same thing. Now U hat AB is a little bit harder to get, right? So let me remind you, what is that? It's going to be RB minus RA divided by the magnitude of that thing, RB minus RA. Okay? So let me try to write out RB, RA, and then we can work out this formula for the force. So I've written down vectors for B and A. So B has no x component, only y and z, and A has only an x component and no y and z. Right? So RB minus RA is given here, right? And to get U hat, AB, we have to just take this vector that I just wrote divided by the magnitude. So minus XA I hat plus YB J hat plus ZB K hat divided by the magnitude of that thing, which is XA squared plus YB squared plus ZB squared. So finally, I can write my force is just that whole thing times F. That's what it looks like. So I've got now my U hat CD is here, my R is here, and my F is here. And so all we have to do now is work out the cross product. I need the magnitude of the moment about that axis is U hat CD dotted with R CA cross F. So I'll do that on the next slide. Okay, so that's the summary of what we've done so far. We need to do this triple product, U hat CD dotted with R CA cross F. And the triple product can be represented as the determinant of a matrix. What goes in the first row are the components of U, the second row are the components of R, and the third row are the components of F. All right, so I'm going to enter in just those components of U, R, and F. Now, just to make things a little bit simpler, there are a bunch of constants which appear over and over again. So like this thing here is a constant, right? It's not, everything is multiplied by that, all of the components. And everything is multiplied by this, divided by that, I guess, and multiplied by this. So I'm going to take out of here all of those constants and put them somewhere else. So I'm just going to put them outside of the matrix here. I'll put here F. And then in the denominator, I've got this big ugly thing of these two square roots, yd squared plus zd squared times xa squared plus yb squared plus zb squared. Okay? And then I will put in the matrix everything that's left over. Okay? So let me now fill out the coordinates UCD. There's no x coordinate. Here I have yd, and here I have zd. And then the components of R, I just have xa here, and then 0 and 0. And finally, I have here minus xa, yb, zb. Okay, now let's do the determinant. So the first thing I do is take this first row, cross out the first row and the first column, and then do this entry times this entry minus this entry times this entry. But the whole thing is multiplied by 0, so I don't need to worry about that, right? So I'll just go ahead and get rid of all those. Okay, so now let's look at the second one. The second one, I take this, and the second row comes with a minus sign. I cross out the first row, this row and this column, and then I take this times this minus this times this. So I get here minus yd times xa zb, and that's it. Okay? And then finally for the third row, I've got plus ZD times XA YB, and that's it, right? So that's the determinant of the matrix there, and the whole thing has to be multiplied by this. So let me just write everything together. Okay, so there you have the formula, and that formula, I know everything in there except for f, right, which is what I'm trying to find. So now all I have to do is solve for f and plug in the numbers. So I'll do that on the next slide. Okay, so I just rearranged the equation, and let's plug in some numbers. Let me just remind you, on the first slide I said that there should be a magnitude here. So we know that the magnitude of the moment is 500, but we don't know if it's plus or minus 500. So I'm going to consider both cases. So we'll have here f equals plus or minus 500 foot-pounds. And then I have to plug in all the numbers for the rest. So let me just plug in those numbers. So those are all the numbers. I just read that from the graph, and let's just simplify it and plug it into the calculator. So that's the result when you plug it into your calculator. Notice all the feet cancels out, so I've got feet to the fourth square rooted, that's feet squared, times another one on the top. So all the feet cancel out. And I'm left with units of pounds, which is good because it's a force. I've got the plus or minus there, but this is the magnitude of the force. It must be positive, right? So we must have 162.03 pounds. So there's your answer to the problem. So I just picked one particular vector, r, going from the line, the axis to the line of action of the force. So you could try and do it with a different one. For example, maybe go back and try the problem again, and for your r, you could take this one, for example, dB. Or you could take dA if you wanted to. You could go like this, right? So try it with a different vector and show that you get the same answer. That should convince you that it doesn't matter which position vector I choose, it just has to be some vector on that axis to the line of action of the force. All right, so I hope you found this problem useful.